Welcome to ISDC. This is the Mars Supplement track. And let's see. We have a series of half-hour papers going to noon. First paper is by Baumann. And are you recording?
Yeah. Well, not right this second, but you can go ahead.
All right. So Irv has been a member of the National Space Society since the early 80s. Helped establish the In-Situ chapter. He helped kick off the X Prize competition with several other students and best members by organizing rocket model launches. Also a member of Planetary Society, Mars Society, moved to LA about 7 years ago and employed in the aerospace industry.
Right.
And pipeline system on Mars. In-Situ.
Yes, thank you, Bruce. It's a pleasure to be here, and hope you had a very successful conference. I was hoping to get here earlier in the week, but work prevented that, so I'm glad to be here to be able to talk. Before getting into this, I want to acknowledge my co-author of the presentation, Dennis Hoppy, who lives in Minnesota. That's my original home state as well. He's a master plumber and provided me with a lot of useful practical information you'll see in here. I'm a lowly electrical engineer, not a master plumber, but but I've had an opportunity to deal with a lot of different engineering disciplines over the years. So again, before getting into this, I want to point out right up front that we're talking about something here that would be designed to support hundreds of thousands to millions of people. So this is in a time frame that I would estimate is at least 200, 250 years down the road. So when the question comes up, why wouldn't we use other ways to supply water to people? Well, we would early on. You condense it from the atmosphere. You'd use tanker truck vehicles to supply smaller numbers of people, tens to hundreds, then even hundreds to thousands with tank trucks if you need to use non-local water. That's the theme of this. However, if you want to start to get into really big populations, there's reasons we use pipelines on the Earth, and there'd be reasons to use pipelines on Mars. And it turns out that ductile iron pipe is a good way to go. Back in 1895, Percival Lowell, as he was thinking about the Mars that he envisioned or thought existed with the canal system of transporting water from the poles to the parched equatorial regions, said this: in the Martian mind there'd be one question, perpetually paramount, the water question. How to procure water enough to support life would be the great communal problem of the day. And that will, I think, be true on Mars as well. If we are not fortunate enough to find abundant and accessible water, below the surface in convenient form, which hopefully we will. But even if we don't, we have these other options. As I say here, ample and readily available supply of water will be critical to support very large civilizations. Not large, meaning again over 1 million people. The northern polar cap, we know, contains enough water to support a population of hundreds of millions, regardless of the availability and accessibility of local subsurface water sources, which again I'll say is the preferred way to go if you can get it, but we don't know for sure. We do know for sure there's water in the North Pole. It turns out that the Martian soil, as everyone knows I think in the room, contains abundant quantities of iron in the form of iron oxide, and also localized deposits of more concentrated hematite iron ore, for example, that we found in the Meridianic Planum with the Mars exploration rovers. And that's the key ingredient for ductile iron pipe, which is commonly used to transport water on Earth. There are methods to cast these pipes that are automatable to a large extent. Centrifugal casting, we'll talk about that. So the bottom line here is that transporting water can be done using conventional methods on a very large scale, obviously. And we've actually already built pipelines on Earth with lengths that are comparable to the distance from Mars' North Pole to its equator, which a lot of people don't realize. Now again, to just say this one more time, and then I'm going to drop it. If you can get the water locally, as we have these indications of widespread water in the upper meter of Mars regolith, that's the way to go. This was adapted from a very good paper presented by Donald Rapp at the last ISDC, and shows the location and of water concentrations. However, the form, quantities, and accessibility of this water is still largely unknown. Okay? So, having said that, if it turns out that we can't get that water as easily as we had hoped, there's still the North Pole and the South Pole, but the North Pole has more liquid water, has more water, frozen water obviously there. There's an estimated 2 million cubic kilometers of water in the North Pole, and if you assume a consumption rate of about 90 gallons per day per person, which is pretty typical, and of course that's total consumption, not just drinking, that's all uses, washing clothes and flushing the toilet. And if you assume that only 10% of the water is converted for use, my calculations, which I double-checked, and I hope I still was correct, is enough water to sustain 100 million people for about 25,000 years. That's just 10% of it. So bottom line is there's lots of water there if we are smart enough to use it and we have enough of a driving need. So the questions are, can we do it? Where do we get the raw materials to make the pipe? What kind of pipe is best? How do we manufacture and lay it? Where do we put it? How much raw material and energy is required, and how do we solve some of the obvious problems, prevent freezing of the water or sublimation of the water, which would currently occur because of the pressures, the atmospheric pressure and temperatures there. There are some solutions. Steam tracers keep the pipe warm, brine solutions, ways to basically have antifreeze in the water that you can then distill out at the end. And the bottom line is we'll have some pressurized pipes. How much pressure is one of the issues with pumping stations at regular intervals. Here's some examples. I'll just show you that this is not totally incredible. The Trans-Alaskan oil pipeline, people think right away, oh, that's got to be, in some people's mind, the longest pipeline. Well, it's actually not, but it's 800 miles from Prudhoe Bay at the north of the northern coast down to Valdez. And it is a 48-inch diameter pipe. It took 6 years to design and plan it, 3 years and 2 months to build, and took about 21,600 workers at peak. So that's all over. That doesn't mean that's all touch labor on the pipeline itself, but there's a lot of people involved. So, 48-inch diameter, keep that in mind. That's pretty close to the dimensions of the pipeline, the inside diameter that I'm going to propose or talk to, as an example. Mine's 42-inch diameter. So we've done that, but more interestingly, here's the Trans-Canadian gas pipeline. The red line represents the distance from the Mars North Pole to the equator, which is about 3,000 miles. And if you stretch this out, it's pretty much a 3,000-mile lifelong pipeline. So we've done that. Now this is a gas pipeline, so it's lower pressures, larger pipes and that. But as far as this kind of scale of piping is concerned, we know how to do it. Of course, it's a lot less challenging environment up in Canada or Alaska than the Mars, but that's one of the things we have to deal with. Okay, as far as what's in the Martian, available in the Martian soil and the regolith, this is a summary, and I'm not vouching, for accuracy to it's kind of some rolled up numbers, but bottom line is this was from Pathfinder data in 1997, yeah. So the iron oxide is about 35%. This is the bulk composition. I think it's reasonable to assume that it's higher in the hematite-rich areas like Meridian and Planum, so obviously you go where there's more ore to mine. However, I wasn't able to find the quantity estimates at Meridian and Planum, but I make certain assumptions, conservative assumptions about the iron content being higher in the places where you would mine it. The sodium and chlorine down here, I've pointed out simply because if some of the examples I have of using brine solutions to lower the freezing point of water uses sodium chloride, and those are relatively small percentages. There's a lot of salts on Mars, as it turns out, in certain areas, but those are a lot of times in the forms of sulfate, magnesium sulfates, which I don't have information on as much as the sodium chloride effects on water freezing temperatures. So as everyone here probably is quite well aware by now, this hematite, which is really an iron ore, was discovered in substantial quantities, at least on the surface and near surface, at the Sinus Meridian Planum. The interesting thing is from my standpoint, and this is just an X-ray spectra showing we've got a lot of iron along with chlorine and bromine and sulfur. Interesting thing is comparing this to Minnesota, where I'm originally from. And here's a quote from Steve Squires, who was the principal investigator on Mars, on Mur, who still is, I assume, because they're still tooling around on Mars. Yeah, in his book, Roving Mars. Hematite can also form in deep basins of water as it has in iron ore deposits in the upper Midwestern United States. So when we talk about large concentrations of iron to mine, Mars has surprised us a number of times, and I wouldn't be a bit surprised that there are some areas that could have far more extensive iron ore deposits than the hematite nodules at Meridiani. This just shows the kind of maps. You have basically a gravity anomaly map and magnetic maps, and you use it to, you can actually see the areas. It's in the Mesabi Iron Range. I'll provide you some information on that. Up in near Hibbing, which is sort of in the northeast portion of Minnesota. And there's several other ranges. There's a Vermilion Range and a Cuyuna Range, but the Mesabi is the biggest one. But my assumptions on which my calculations are based are actually not assuming we have these extremely large concentrations. It's assumed that we have a Martian soil with a little bit more than the 35% iron oxide in it. So I'm not making assumptions that this kind of stuff exists on Mars, but I wouldn't be surprised if it does. This is an open pit iron mine in the Hibbing area of the Mesabi Iron Range, Minnesota. Largest open pit iron mine in the world, although others claim the same thing. It's been in operation since 1895. 3 miles long, 2 miles wide. Of course, it kind of varies, but those are the maximum. 600 feet deep, so it's about 100 billion cubic feet. 1.4 billion tons of earth have been removed. Most of them have been closed. There was like 30 separate operations going on in there. Most of them closed in 57, but they're still producing now a lower grade taconite ore. You can see the kind of machinery in the upper right there that's used. Big stuff, obviously. You'll find out also that when I show you what needs to be excavated on Mars to do those 4 pipelines I propose, is far, far less than that, about 1,000 of that. What kind of pipe are we talking about? Ductile iron pipe. Okay, ductile iron ranges in iron content from 96 to 100% with 4 to 0% carbon. The more iron and less carbon, the better, the colder it gets, which is nice because carbon is hard to come by, takes some work to get on Mars. So it's kind of nice that basically a pure iron pipe would be almost preferable. They already have what they call river crossing pipe, a jointed pipe that you can go over down the riverbeds and up and traverse uneven terrain, which obviously is an issue. And I'll go on to centrifugal casting. This is one of the techniques that would be that's used now, and that could be automated on larger scales, where you spin up the chamber and you have the molten iron in it. And as you spin it, you also get separation of some of the oxides and impurities. Getting the oxide out is a big part of this. Of course, you also actually use arc heater-based furnaces to drive out the oxides. But this also does a separation as it's spun up of some of the remaining oxides and impurities. So that's something also that can be used in an automated fashion on Mars. Now, there are pipe laying methods. Machines, we have obviously identified on the left here, more manual methods. The problem-solving skills of people are essential. The upper left one, I believe, is the section of the Alaskan pipeline under construction. We also have pipe laying barges that they lay into relatively deep water, and we have railroad track laying machines that I think could also be adapted to perhaps being some kind of combined centrifugal casting and pipe laying machine. Who knows? I didn't go that far as to actually design it, but this is just food for thought, okay? Again, the theme is we have done things on this kind of scale here, and if we can do it with iron, we have a shot to use in-situ resources on Mars to do this. Now, here's an example. I'm going to go into an example based on some real data from a real water system. St. Paul, Minnesota, my hometown. This is where where Dennis also worked as a plumber for many, many years. Found this information out. The pipeline system there services about 400,000 people. The greater metropolitan area of the Twin Cities is much, much larger than that, but the St. Paul area and the suburbs that this serves is about 400,000. Again, they use the 90 gallons per person per day. They have a 42-inch inside diameter ductile iron pipe. It's the main feeder line, okay? There's a lot of smaller ones, 18-inch, 24-inch pipes off of that, but the main feeder line is 42-inch ID. 3/4-inch wall thickness. That operates at 90 to 100 psi. I don't think we necessarily have to do that. Of course, that's related to flow rates and things. Oh, and by the way, on the 90 gallon per person per day, I'm going to be making assumptions later on that on Mars we do better than that. That's kind of, fairly inefficient, and there are indications we should at least be able to get by with 45, 50 gallons per day with some recycling and things like that. The main pipeline length is about 50 miles, and they have pumps located every 25 miles. Now, here's the first big power shocker figure you see. The power per pump was about 1,750 horsepower, which translates to about 1,100 kilowatt electric. So right there, we're already in the megawatt range. So power is paramount for this and just about any large-scale, production process on Mars. So we'll talk more about that later. This system can deliver about 35 million gallons per night, which works out to be about 400,000 times 90 gallons, to replenish water stored in local towers and reservoirs. So that's another part of this that I don't really go into in detail, is designing of reservoirs, but you would do that kind of a thing so that overnight when your water utilization is low, you replenish that and you draw down your reserves during the day. Okay, the raw materials required for this proposed system. And I won't bore you with the calculations. I have a spreadsheet if anybody wants to look at it. 42-inch inside diameter pipe with 750, 0.75-inch wall thickness. Okay. 4 3,000-mile pipelines from the pole to equator at locations I'll tell you about later. Why did I pick 4? I don't know. Just kind of thought it was a good number and was more interesting than just looking at one. I'm assuming a terrain roughness of about 20%. In other words, you have to move about 20 feet to accommodate the terrain roughness for every 100 feet of length you move in the desired direction. So that could be up, down, left, right, whatever. Anyway, the iron concentration in the mine soil, I'm assuming 50%. 35% is average across the entire planet. I would think certainly we could find local areas that the concentration is on the order of 50%. Now, the results are that the area that must be excavated for this is about a half-mile long, a half-mile wide, and only 15 feet deep. Okay, which is about 1/1000th of the Hibbing Masabi open pit mine. So we're not talking about something that is going, that is on a scale that's unimaginable. Right now, I guess it is. But in a couple hundred years, I don't think this is out of the question. So I could give you the billions of cubic feet, but I don't think I put them on the chart. But the bottom line is to compare it to the open pit mines that we've had in operation for 100 years, about 1,000th of that. What are the power requirements? Well, the nuclear power, when you add it up, is pretty much essential at 100 megawatt levels. And of course, a lot of nuclear reactors range from, on Earth, from 50 megawatt to 400 megawatts, with most of them clustering in the 100 to 150 megawatt range, but that's pretty big. You need to power the mining equipment, electric arc furnaces to separate the oxygen from the iron, to do pipe fabrication and laying, and for pipeline operations. The assumption here is that
About 4 minutes.
4 minutes? When I estimate that pumping stations would require every 250 miles instead of 25 miles, we'd be operating at lower pressures. We also have, we'd be going downhill in large part too. Because we're going from the pole down to the lower elevations. It's about an 8-kilometer drop over 3,000 miles, which doesn't sound like a lot, but it actually helps a lot. Each pumping station would use about a megawatt, so that's 12 megawatts per pipeline. Heating requirements would increase this. Obviously, there's power distribution, generation challenges. As far as salt brine is concerned, we can use the salt brine to lower the freezing point to help us out. And this shows you, you can get down to about a -6F freezing point at about 23%, 22% by weight for sodium chloride. So the salts could be useful, but most abundant salts appear to be sulfates, not sodium chloride. The phase diagram for water, I just want to make a point here that the Mars pressure and temperature is actually close to the triple point of water. So we might have an option to actually pump water as a liquid or a vapor. Now, if you're doing it as a vapor, that makes, or a gas fog, basically, through the pipeline. It makes things much, much easier. You're basically piping or blowing supersaturated fog from the pole to condensation stations at lower latitudes. But, of course, the volume that you're transporting is much, much less. But that's something to look at in the future. Mars' northern hemisphere is low, relatively flat, slopes down from the North Pole to lower elevations, so that's where we would be going. And here I want to leave you with a kind of a little interesting thoughts. Percival Lowell's Martian Canal system, they actually went so far as to name some of these canals, so I went and looked that up. It was kind of fun. So Sirius, Aces, Castor, Drahonis, Ra, Hades, and Hillis. These are the locations that I picked based on the general elevation and also the probability in my very crude estimate of ore deposits associated with certain geological features, or areological features, I guess I should say. So I gave them names, but there's 3 of them in the Western Hemisphere and 1 in the Eastern Hemisphere. And the concluding thought I want to leave you with is that if we do, sometime in the next couple centuries or so, proceed to do this sort of thing, it's almost certain that you would have towns built up along the pipeline way, so you wouldn't just have a town at the beginning and the end, you'd have some other nodes along the lines, and you'd want to interconnect them. And it's very conceivable that a version of Lowell's vision could come to pass after all, and you would have water being sent from the poles to the dry southern regions, and it would be built by Martians, but the Martians would be us. So each pipeline would support, and so the other thing I didn't say, that the example was supporting 400,000 people on Earth. If we just reduce the water consumption to about 50 gallons per person per day, and we can also make some other adjustments that could make each of these pipelines support on the order of 1 million people. So that's all I have. Any questions?
Thank you. Did you give any thought to using the nuclear reactor waste heat, using water to cool the reactor by so that when heating it, send it through?
That's a very good idea, and I think that we'll have to get clever in a lot of ways to very efficiently use the heat that's around for other reasons, and and certainly as long as you can avoid doing bad things to the water when you're using it as a coolant in the reactor.
Not the primary.
Not the primary loop, right? But no, I think that's a good point. I'll make one other point too. People talk about drilling. I looked into drilling for oil and other things through permafrost in Siberia. They've drilled to quite deep depths for water. But guess how they do it? They use a steam heat. They use a pipe within which the drill is, and they blast super hot steam down there. Well, you got to generate that somehow too. So even if you don't do this, if you're going to try to get large quantities of water out of the Martian soil locally, you're still going to need a lot of power.
Well, I think your idea of sending vapor, which you could do for made of very thin film material.
It becomes a duct.
Yeah, really you ought to look at that for next year.
Yeah.
Fascinating to see how that works out.
And we can see how much that would increase the efficiency of the atmospheric condensers you could use just on the ambient air by sending this super
You
saturated
can
film.
keep it heated just with the solar mirrors along the pipeline.
Right. And that might fill a nice gap too in terms of the number of people that can be supported.
Right.
It's scaling up from the local condensers that might support tens of people to something that would support hundreds of thousands as a step along the way. Question back there?
Would you be worried about corrosion at all?
That's a good question. That's one I wanted to go into more deeply on too. Turns out that there are certain treatments for the inner surface of these pipes, and That's kind of a loose end, because it's possible that that would take, additional steps or materials that are problematic. But in fact, when you look at that pipe too, they showed it wasn't a iron, reddish pipe, it was black. They had some treatment on the outside of that, even though, that might have been partly the carbon content. But so that's a good point. How, over what period of time do you end up, adding large iron content to your water as it flows through?
Even though they treat pipelines here, they still are quite concerned about corrosion, and they do regular inspections and whatnot. So even though you treat it, it can still be a problem.
Yeah, and that's another part of the infrastructure that would have to be considered too. If you have this regular, you want to send some kind of a, what do you call it, pig or something, send some kind of a cleaning device down the pipeline. How do you do that? So, right.
Would you disconnect your laptop?
Yes, no problem.
At least
From the video, yes.
In your research, did you learn what the largest piece of centrifugal, large diameter centrifugal cast pipe piece of done might be? I'm just curious to know from the standpoint of making pressure vessels on Mars.
Yeah, I don't have that number, but I do remember when I was looking at getting the information on centrifugal casting, that there were some pictures of the pipe that were, I'd say, at least on the order of 32, 36 inch diameter. Now that was, they didn't flat out say this machine made that pipe, but the implication was that it could go fairly large. But I don't have any definite proof that it could do a 42 inch pipe.
Or 5 meters diameter, right?
Oh,
It might be pretty good.
yeah, yeah. Well, I didn't need. Well, in the case of, if you start talking about doing sending the fog, the vapor, you can start making some pretty big things that are like you said, pretty thin walled.
Right, I was
And
thinking in
other
terms of
techniques.
not pipe, but pressure vessels for habitation purposes. Just casting.
Yeah, that's an interesting thought, but yeah, I haven't looked into that further, I'm afraid. We'll need this power down here as we get to the next person. Thank you very much.